We've had science for, let's say, since Newton or Copernicus, 500 years at most. And look what we've done. We've gone beyond the solar system with Voyager. We've walked on the moon. We're about to go to Mars, I would think. So we're about to begin colonising our own solar system. We've done that in 500 years. So imagine a million years in the future. It's one of the arguments often used to say there aren't any civilizations out there in the galaxy. It's called the Fermi paradox. Because if you imagine a civilization that's a million years ahead of us, they should have written their presence across the sky by now. You should see them. I mean, you'll see us. If we survive a million years into the future, actually even a few thousand years into the future, we will be exploring the galaxy. We will have spacecraft that are going to other stars. We will be doing it. So our signature will become visible, I'm sure, if we last.
Like if there is a civilization that's a million times more advanced than us and been around here for, millions of years of life as opposed to 250,000, why would they let us know? Like would they look at us dropping bombs on each other and polluting the ocean and sucking all the fish out and putting clouds into the skies of dirt and particles? And why would they look at these crude monkeys? Look at that. They're so far beyond where they need to be before they could join the galactic civilization network or whatever.
It is true. It's an argument that there is an argument as well that technology so advanced would be difficult for us to detect. I mean, we tend to think of, when you say written across the sky, I suppose it's true. I'm thinking of starships and things like Star Wars, right? Big energy things that you can see the signature of. But actually, it may be that the civilization just becomes a nano civilization, tiny little nano, but because that's more efficient, it's a better way to do things. So it's possible, I suppose, that there are space probes all over the place that are so small and are so efficient and use so little energy that we just don't see them. This is one of my favourite photographs of the Milky Way. It's taken from the European Southern Observatory in Chile. In the southern hemisphere, they're fortunate because they're pointing towards the galactic centre. So the rich star fields of Sagittarius are visible. The top of this arc is the centre of our galaxy, obscuring a supermassive black hole, 4 million times the mass of the Sun. We're looking at a galaxy with 200 billion stars or so. We now know that most of those, if not the overwhelming majority, have solar systems. The current number for the estimate for the number of Earth-like planets in that galaxy, that's rocky planets, the right distance from their star to potentially support oceans on the surface, is of order 20 billion. So we're speaking about, in terms of 1 in 10 stars in the Milky Way having a potentially Earth-like planet around it. Now, we can't, of course, see the structure of a typical galaxy from within. We have to step outside. And when we step outside and start to look at local galaxies, the scale of the challenge for trying to understand the universe, I think, becomes clear. And this is a photograph of a nearby galaxy, one of our local neighbours, about 23 million light years away. It's called the Whirlpool Galaxy. You can see this actually with a relatively small telescope, a 4 or 5 inch telescope. But the scale of the photograph is challenging. It's about 100,000 light years across, which means light traveling 186,000 miles a second takes of order 100,000 years to cross this photograph. It's also interesting because it's a photograph of an interacting galaxy. So the little yellow blob there on the right is a smaller dwarf galaxy, which is distorting the spiral arm, causing increased rates of star formation in that arm. So although the galaxies are relatively sparsely distributed across the universe, they're not so sparsely distributed that they don't interact with each other. We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed and you know how many galaxies you've counted, and then you can spread that across the wider universe. And you get this picture of a vast and possibly infinite universe. I mean, we know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. This is a visualization of real data. It's a visualization of the Sloan Digital Sky Survey. which is a project to map the positions of relatively local galaxies in the universe. So although in this animation the points are exaggerated so you can see them, the distribution of the points is correct. So this is a fly-through of the local universe. And you see, at first sight, it just looks like a snowstorm, a random distribution of galaxies. But in fact, it isn't entirely random, or it's random in a very particular way. When you look more closely, you see that there are sort of rivers and flows of galaxies. There are voids where there are fewer galaxies and areas where the distribution of galaxies is more dense. And that is indeed telling us something about the formation of the galaxies, the processes that seeded the distribution of galaxies in the sky. And that's telling us something about events that happened very much closer to the origin of the universe when there were no galaxies. The overwhelming sense that I certainly get from looking at visualizations like this is that the universe is big. The current estimate for the number of galaxies, large and small, in the observable part of the universe is around 2 trillion. And it seems to increase every few years when more data comes in. But if you think about even the observable piece of the universe containing 2 trillion galaxies, I think the ambition of cosmology becomes clear, the ambition to understand where all that came from and how those structures emerged in the universe is a tremendous one. One thing we can say is, notwithstanding the size and scale of the universe, the Earth currently is a special place, albeit physically insignificant, because it's the only place we know of in the universe that supports life. Now, we strongly suspect that it will not be the only place in a typical galaxy like the Milky Way to support life. But what do we know about the possibility that civilizations themselves are rare? Think about the history of life on Earth. The Earth formed about 4.5 billion years ago out of the cloud that formed the Sun and the rest of the planets in the solar system. And what we do know is for the first 500 million years or so, the Earth did not support life. It's called the Hadean Epoch. It's a time when there were no oceans on the surface. The Earth was too violent a place to support oceans, and therefore it was a dead world. But what we do know is that pretty soon after the Earth cooled down and the oceans formed, so around 4 billion years ago or so, life began. The transition from geochemistry to biochemistry happened here on the Earth. And given that happened pretty much as soon as the oceans formed, I think many biologists suggest there may be a sense of inevitability about the origin of life. We will test that, I think, in our solar system in the next few years by looking for life subsurface on Mars, life on the moons of Jupiter or Saturn that have oceans below the frozen surfaces. So it's a testable hypothesis. But I think that a guess may be that simple life, at least, may be relatively common throughout the universe. I don't see any reason why AI is in principle not possible. I think that although the research, we don't understand the brain, but I think it must be an object that operates in accord with the laws of physics. I strongly suspect that our conscious experience is emergent, so it emerges. So there's an algorithm there, a very complex algorithm, but I don't see why it can't be simulated in a sufficiently powerful computer in principle. So I don't see why you can't have a conscious computer. I don't personally see why you can't. Therefore, if that's true, then you can, given them. And as you say, the rate of increasing computing power is rapid. We're not there yet. There is a project in Europe, a very big project to build a brain simulator. It's a long way off, and you're talking about billions of dollars. But at the moment, as you say, that 40 years ago, $1 billion wouldn't have bought you an iPhone. 3D printers essentially seem to be the first step on the road to a self-replicating machine. So you've got the computing power that can be intelligent, and you've got a means of it being a replicator, then I don't see why you can't build AIs that replicate. And actually, going back to the cosmology for a minute, one of the arguments against the existence of civilizations, more advanced civilizations than us in the Milky Way, is that they would have done that. And this is an argument from a mathematician called von Neumann, and also a physicist called Fermi. It's called the Fermi paradox. Let's fast forward our civilization 10,000 years, let's say. Blink of an eye. Let's see. We've been around for less than that as a civilization. Let's double it, 10,000. What are we going to look like? Will we have built self-replicating AIs? Yeah, unless there's some reason in principle why you can't. So what do? You send those out. They're replicators. They can go to asteroids, mine, print, 3D print a version of themselves, go off again. They exponentiate. They can crawl over the galaxy, exploring for free. You send them out. We see no evidence of those things. They're called von Neumann machines. So it's one of the great... You can either say that there's something in principle that stops you doing it. So actually there is something special about intelligence, and you just can't... There's some reason why you can't build a computer that's artificially intelligent. I don't see why that would be the case. Or you could argue you can't build a self-replicator, but you can, because we are replicators, and we operate in accord with the laws of physics. So there's a replicator. Or the reason we don't see them is because there aren't any civilizations that ever got to that level in the Milky Way.
So we're the tip of the spear.
No one... Well, we couldn't be the first. It's very difficult to see how we could be the first.
Someone has to be the first. Why can't it be us?
But because the Milky Way has been around for the age of the universe.
So you say. So, don't you know the Earth is 6,000 years old? Do you not go online?
Putting that aside. So the timescales, we're talking billions of years.
Right.
Billions of planets, billions of years.
But it has to happen one time, somewhere.
And then and if you get one wave of these AIs away into space, then you can show, using computer models with realistic assumptions about rocket power and things like that you can cover the galaxy on timescales of much less than a billion years, actually million years, less than that. So you can show that you can cover the galaxy in your von Neumann probes, your replicators, in hundreds of thousands of years. Let's say 1 million, 2 million, 3 million, 10 million. Doesn't matter, because we've got billions of years, and yet we see no evidence of them. So what are we to make of that? Either there's something wrong with our argument that we're putting forward, that actually you can't build self-replicating intelligent robots. I don't see why not, but maybe there's something wrong with that. Or really, civilizations are so rare that, as you say, we are the first to get to that level. But that's interesting, isn't it? That would be an interesting... I always think in a almost Sagan-esque sense of this. So imagine we're the only civilization in the galaxy. What a tremendous responsibility there is on us. Imagine what that knowledge should do to our political processes, the way that we think about ourselves, the way that we get on together. Imagine how ridiculous it is to divide our little world up into countries and have a little war every now and again and point nuclear missiles at each other. If in fact there's nowhere else in the Milky Way galaxy where anybody thinks, where anybody can look at the stars and think about and have these conversations. What a ridiculous way to behave. So I think cosmology gives a perspective which doesn't necessarily need to be humbling. It is humbling, and that's perhaps a good thing, but you don't need to be depressed about it. It could be quite elating. You say, well, what we are, according to the evidence and the data at the moment, is almost indescribably special. Our tininess, our potential uniqueness, our insignificance in a cosmic scale actually makes us special because we're the only place. And so these ideas are worth pursuing, I think, because they make you think about these issues. If you ask the question, when, after the origin of life 4 billion years ago, when did complex life appear? Then you have to wait essentially 3.5 billion years. You have to look to only 500 million years ago or so for any evidence of complex life on Earth. Before that, you just get single-celled organisms. This is a photograph of structures called stromatolites, like those found off the western coast of Australia. Single-celled colonies of photosynthetic bacteria at best. You get the first evidence of complex life on Earth in fossil fields such as this. This is the Burgess Shale in Canada. It's also interesting to note that green Earth in that photograph, the Earth that we know today, the blue oceans and the green plants on land, the plants didn't colonize the land until less than 500 million years ago. So the question may be, why is that? Does that tell us something about our position in the universe in terms of consciousness and civilizations? Biologists point to some things that may have happened in that evolutionary journey, or that journey from the single-celled origin of life through to complex life and civilizations, that may be bottlenecks. One, for example, it's often called the fateful encounter hypothesis, is the origin of the eukaryotic cell, the cells out of which we and all complex living things on the planet are made. That appears to have happened once in something called a fateful encounter in an ocean about 2.5 billion years ago, when one cell got inside the other one, which is difficult to understand how that could happen and continue to live, but it seems to have done so. In particular, a bacterium seems to have got inside an archaean. But then, not only did that thing survive, but even more miraculously managed to reproduce and perpetuate that configuration. That seems to be a very unlikely thing. Without that single event at some point 2.5 billion years ago, it is likely there would be no complex life on Earth today. So the question arises, well, on how many worlds not only did life begin, which, as I've said, the suggestion may be on many, but on how many did that life become complex, let alone develop consciousness and build a civilization? Well, I was talking to a friend of mine at Manchester, a biologist, and I showed this picture in a talk I was giving, which is, I don't know if you can see it, but it's a beautiful photograph of the Milky Way. It was, again, put together by the European Southern Observatory, actually, from photographs all around the Earth. So this is the whole sweep of the Milky Way across the sky. And he looked at that and said, in that galaxy, I think, at best, there is only slime. That was his view as a biologist looking at the history of life on Earth. If that's true, then it puts our insignificance, I think, in a very different perspective. From a cosmological sense, it may be that the Earth is the only place in this galaxy where people like us can think about science and do cosmology. And even if that's not the case, it is true to say that we've looked a little bit and found nothing. It's often referred to as the Great Silence. And I would argue that one of the profound messages that cosmology and biology together give us is that we may as well proceed on that basis. If we proceed on the basis that perhaps we're the only civilization currently present in that galaxy, then I think we may behave a little bit differently to the way we do today. So that's a perspective, I think, that biology, when merged together with cosmology, can give us. Cosmology itself, though, as I said at the start, it's challenging us to think about origins and evolution of the universe. In order to do that, we need more than observation, we need a theoretical framework. The theoretical framework, I'm aware that I'm speaking to an audience which is almost half general relativists and cosmologists, is Einstein's theory of general relativity, published in 1915. I often reflect on the fact that it's an unusual thing, or a surprising thing at first sight, that a theory that's developed as a theory of gravity becomes a theory of cosmology. It wasn't designed to be a theory of cosmology initially. If you look at how the universe is expanding at the moment, then it is accelerating in its expansion. So the measurements tell us that the expansion rate itself is getting faster. And we have a name for that. We call it dark energy. So and of order 65-70% of the energy in the universe appears to be taken up in driving this increasingly fast expansion. And so that looks like, if nothing happens, then that becomes dominant. So it continues to accelerate in its expansion, and in the end you get something that looks like this inflationary period that I said may have existed before the universe was hot and dense. So it looks like that looks like what's happening at the moment. So whether that can stop, whether there's something that can stop it in the same way as it seems to have stopped very early in the history, by the way, and whether that's true, nobody knows. We don't know the mechanism, but the measurements tell us of distant, particularly of looking at supernova in distant galaxies, and also actually from this cosmic microwave background radiation. The detailed modelling and measurements of that all are consistent and suggest that the universe is accelerating in its expansion. So that would suggest that it's not going to rebound, because it's like a big rip scenario almost, where everything's accelerated. Space-time is stretching at a faster and faster rate at the moment. That seems to be what's happening. Inflation is probably textbook now. You get some physicists that will argue with it, but broadly speaking, I think many astrophysicists think that inflation's the best theory we have, because it makes predictions that agree with observation. So it's the best theory in terms of making the best predictions at the moment.
And this is that
suggests that
its
very
expansion,
very fast, superluminal, faster than light expansion that stops, and the end point of that is what we used to call the Big Bang. So that's, broadly speaking, textbook stuff. That's what you teach in undergraduate cosmology courses. Then some physicists argue that the natural extension to those theories, a theory is called eternal inflation. This exponential expansion of space-time is always going on, and it stops just in little patches, and that little patch is where you generate a new pocket universe, if you like, of which ours is one example. And you can have an infinite number of those, and they would be being produced now. And you can ask the question, how long has that been going on? And the answer is nobody knows. And there's a debate, even amongst the people who believe in those theories, about whether it could have gone on forever, or whether it would have started in what a colleague of mine at Durham, Carlos Frank, calls the mother of all big bangs. So was there a mother of all big bangs that set this process in motion? And in that thing that got that big fractal thing, you get loads of little big bangs. And the answer is this is cutting edge stuff. It's very exciting. So I'd say, just to be very precise, the inflationary bit, the simple bit, which was first put forward in the 80s, actually, by Alan Guth and people like that in the US. Andre Linde, another one. That looks right in the sense that it matches data very well. And the consequences of it are argued about and are active areas of research at the moment. The inability of some people to understand evolution and react against it, it's all actually just religiously motivated. Most of it is, but some of it isn't. I think there's also a lack of understanding of the timescales involved and how fast animals can adapt and change, and what a powerful sieve, if you like, evolution is. You can see it. Richard Dawkins often when he's writing beautifully about these things, writes about look at domestic dogs and look how quickly the wolf got turned into these somebody from poodles to German shepherds to whatever it is, all those things. That's selection by humans, right? So we're selecting for particular traits. But the environment and the interaction with other species is as powerful as that. It's as efficient as that. The environment is a very powerful selector of traits. And so you can see that evolution happens quickly. Speciation happens quickly. And not quite with the dogs, they're still the same species. But you can see how, given a bit of time, you're going to get the poodles and keep going on that line, and get the wolves and keep going on that line. And eventually you're going to get things that look so different that if you separate them and don't let them interbreed, that you're going to end up with something that can't breed with that anymore. And that's kind of the definition of a new species, one of the definitions of a new species. So you can see how it can happen. It's obvious. And I think one of the problems is the timescales are not understood. When you talk about thousands of years, that's quite a long time. 10,000 years is a long time. 200,000 years, you go back that long, and we didn't exist as a species. We weren't there. So hundreds of thousand years is a hell of a long time.
I read recently was that black holes aren't real. Is that nonsense? Is that like one person's controversial idea?
Yeah,
basically.
So it's not necessarily nonsense just because it's one person's idea, but it's likely to be nonsense. I haven't seen that particular theory, so I don't know. I mean, we have a lot of good evidence for the existence of black holes, not least they're predicted. They're a prediction of Einstein's theory of general relativity. They're on solid theoretical ground, and we've seen the signatures of them. So, for example, the objects at the centre of the Milky Way galaxy. We know what the mass is of that object because we've measured the orbits of stars very close to it. We know what the maximum size of the object can be because it can't be bigger than the orbits of the stars that go around it. And so we measure its mass. I think it's about 4 million times the mass of the Sun. And the only way that our current laws of physics allow such an object to exist and be so small is for it to be a black hole. So there's good evidence that black holes are around. But you can always say, well, we haven't been to one. They're very hard to photograph because they're black. But you can photograph the stuff that falls into them. You can see the signature of stuff falling into them, which we do.
And they've what was it like? It was the somewhere in the 2000s they figured out that at the center of every galaxy is a supermassive black hole that is like 0.5% of the mass of the galaxy.
We think so. As I said, I think so. Off the top of my head, I think it's about 4 million times the mass of the Sun.
And so the larger galaxies would have a larger black hole.
I'm not sure if it's that. It's not well understood, actually, because it's not well understood how galaxies form in the first place. And what role these supermassive black holes have in the formation of the galaxies. So that's a real active area of research, actually. It's a good question.
The thing that I was reading was they were debating the possibility that inside each one of these supermassive black holes, so like there being hundreds of billions of galaxies, each one of them with a black hole in the center of it, a supermassive black hole, in through that black hole is a whole nother universe with hundreds of billions of galaxies, each with black holes. Go through that whole 100 billion more galaxies, each with black holes. Go through that 100 billion more. I mean, that each galaxy itself literally is a portal to a completely different universe.
I mean, the point, we don't have a
right.
The problem with black holes is that they're a prediction of Einstein's theory. One of the earliest predictions is a thing called the Schwarzschild metric, which describes black holes. It was done, I think, in 1915 or 16. It's right as soon as relativity was published. It was shown that these things could exist. But we don't. The theory itself breaks down. Then
the theory of black holes,
the general relativity, which is the theory that explains Einstein's theory, which sort of predicts their existence, but it doesn't. The characteristics of black holes, the physics inside black holes, is not understood. We don't know. Our theories don't work. We need what's called a quantum theory of gravity to make progress there. So that's the unification of quantum theory and relativity. And general relativity, which is what string theory is an attempt to do, but we don't know whether that's the right theory. So this is the edge of knowledge.